This video is for Math 1325, and we're going to be going over the first review today. The review does count as a grade. I get that a lot. The people claim later they didn't know it was a grade. Review number 1, test 1, major homework grade. So it counts equal to all these other homeworks combined. So if you do find yourself running out of time, it's better to do the review and miss some of these homeworks than to do all these homeworks and not do the review. But everything from 2.1 all the way to 3.2, and the review, those are all due Friday, September 23rd, 11:59 p.m. So if you're keeping pace with the calendar, hopefully you're doing section 3.2 in the first half of this fourth week of the semester, and then in the second half of the week you can work on the review as much as you like. It has an infinite number of attempts, and only the highest grade counts. So many students will just do it once and not even maybe finish it all, and they just run out of time, and then they try taking the test anyway, and then they get a bad test grade. So ideally you can do this at least once, if not more than once, and maybe do one practice run right before you take your test. And if you can do the review in one sitting, the test has a time limit, so if it takes you a long time to finish a review just to get a good grade for it, that's fine one time. But the test has a limited time frame. They're all either an hour and a half or 2 hours, depending on the number of questions and how long questions take. So once you open your test, the time starts counting down, and then that's your only chance to do it. So it's good to take one practice run of the review, treat it like a test run where you limit yourself to an hour and a half or 2 hours and see how you do on it. Okay, so all of the review and test questions are similar to homework questions. So the review is not identical to the test, but it's close, and it's all from homework problems. Now the review, my math lab thinks you're taking a quiz. So that doesn't have all that help the other homework had. Like there's no help me solve this, view an example. You can't check each answer. So you have to work all 25 questions out, and you don't have to do them in order. You can skip around. But one time you need to work all 25 questions out and then submit it. Don't submit it till you're done, and then you'll get a grade for it. If you're not happy with that grade, unfortunately, you'll have to redo the entire review, even the problems you got right, to get a better grade. But that's not the worst thing in the world, because that helps you get ready for the tests better. The good news, though, is once you do reach a grade you're happy with, if you do this once and get a 95 and that's good enough for you, then you never have to do it again if you don't want to. But what you could do is then you could just do some of the problems. So you could try the review a second or a third or a fourth time, and even if you just did one problem or 2 or 3 problems, then you could submit it and get a terrible grade for that attempt, but only the highest grade counts. Okay, list ordered pairs. This is taking us back to section 2.1, so we're back to basic algebra stuff. List the ordered pairs if you use 0 through 5 as your domain, and then graph them and give the range. Okay, so the ordered pairs is basically the domain and the range. When I plug 0 in for the first domain number, put a 0 in for these two x's, 0, you do the parenthesis first. 0 plus 1 is 1, and 1 times 0 would be 0. So when I plug 0 in for the domain, I get 0 for the range. And that's one of 6 ordered pairs. And each ordered pair, we already know how they all start. The next one's going to be 1 comma, then 2 comma, all the way to 5 comma. Plug 1 in. 1 plus 1 is 2. 2 times 1 is 2. Now we plug 2 in. 2 plus 1 is 3, and 3 times 2 would be 6. Plug 3 in. 3 plus 1 is 4. 4 times 3 is 12. Plug 4 in. 4 plus 1 is 5. 5 times 4 is 20. And finally plug in 5. 5 plus 1 is 6. 6 times 5 is 30. So I just need to plot these 6 points, and sometimes, most of the time actually, a graph is continuous and has a line through all the points, but this is a very limited domain. I just have these 6 values only. So then the graph only has 6 points on it. And 0, 0, 1, 2, 2, 6, 0, 0. This one doesn't even have 0, 0. This one doesn't either. So it's obviously graph B, 0, 0, 1, 2, 2, 6, and then 12, 20, and 30. So graph B is the only one that has all the points correct. And then the range is just the y values, and we typically list it in order from lowest to highest with no repeats if there are repeats. The domain can never repeat, but the range can repeat all you want, so that doesn't really matter if it repeats or not. 0, 2, 6, 12, 20, and 30. And we list that just like the way the domain is listed. So the domain has the squigglies 0 through 5, and now squigglies 0, 2, 6, 12, 20, and 30. All the y coordinates. So we don't know if this answer is right until the end. So instead of submitting it, I could submit it, but then I'll get only possibly 1 out of 25 points, which is 2.5%. So the best I could get is a 3% if I submit this now, but I'm going to, over here on the bottom right, I'm going to hit next. Don't hit submit till you're ready to grade it. So we won't know if it's right until it gets graded at the end. But this is good practice for a test, because when you're doing homework, if you make a mistake, it says wrong, and then it gives you a chance to correct it. That doesn't happen on a test. So in a test, you never know if it's right till the end. So this is a good practice for a test to do this review at least once. Okay, see, here's a more normal graph where we have lines drawn, or curves potentially. So then every point on this line is part of the domain. You could literally never list the whole domain because there's an infinite number of points. So instead of listing all the individual x's, we list them in interval notation. And this graph could have an arrow going down and to the left forever, but it has a point there where it starts exactly at that spot. So domain are x's, range is y. Domain is how far left and right can you go. Range is how low and high can you go. The farthest to the left I can go on this shape here is this point, which happens to have an x value of -3. And because it's a closed circle, not an open circle, then we include that spot. So we would put bracket for -3. If it was an open circle, I would put parenthesis for the -3. And then I can travel as far to the right as this point, which is an x value of 6. And it does hit it exactly because of the closed circle. So the domain is literally all x values between -3 and 6. You can reach any x between -3 and 6, but you can't go further than 6 or less than -3. Then as you go up and down this shape, the lowest you can reach, it happens twice, but that's okay. If there's a tie, that's fine. We get as low as a y of 0. The x-axis is a y of 0. The lowest I can go is 0 exactly. And the highest I reach, I do it twice here and there, but it's a tie, that's fine. 6 is the highest I can ever go. It never goes higher than 6. So domain is left to right, range is bottom to top. And then we can evaluate 3 specific points. When f of -3 means when x is -3, what does the y equal? When x is -3, you're exactly at a y of 0. When x is 0, which is right at the origin, the y, you'd have to go up here to touch the graph, the y is 6. When f is 1, when x is 1, I'm sorry, when x is 1, then f of x would be right here. F of x is the same thing as y. The y value would be 4. Or you can do this backwards, which is what the last part wants. What are the x value or values when f of x equals 2? If f of x equals 2, f of x is the same thing as y. So we're looking for x, and we know y is 2. Y is 2 right here. But if I go left, I can touch that spot. If I go right, I can touch here and there. There's 3 different x's that have that same y, and it's okay if the y's repeat. So -2, 2, positive 2, comma 2, and positive 4, comma 2. They would have 3 unique x's, but they would repeat their y's, and that's fine. And they don't want coordinates here. They just want you to separate the answers with a comma. So x could be negative 2, 2, or 4. And then your y would be 2 in all 3 of those locations. So that's question 2. Okay, function notation. G of x is x squared minus 5x plus 6. Write that down. G of x is x squared minus 5x minus 6, or plus 6, sorry. X squared minus 5x plus 6. We're looking for G of r plus h. And typically it doesn't matter what we're plugging in. We just take whatever they give us and plug it in. So we're going to literally plug r plus h in to each x. We don't care how messy it gets at this point, but those x's disappear and get replaced with r plus h. So instead of x squared, I get r plus h squared. Minus 5, and then instead of this x, I replace it with r plus h. Plus 6. This one's kind of arbitrary to have r plus h, but we do a similar thing when we're doing those difference quotients that are a big part of algebra, or a big part of calculus eventually. So r plus h squared, there's a nice shortcut to this. Since we do this so much, you should get used to this shortcut. If you have to do it slower, that's fine. But remember, on a test with a timed limit on your test, any shortcuts you can use can definitely help save time for other problems. So you square the first term, r squared. You multiply these two things together, and sometimes one of them's a number, but here they're both variables. If I multiply RH together, it's literally RH or HR, however you want to write it. And then that actually gets doubled when you're doing a binomial squared. So I'm going to get 2RH or 2HR if you want to put it alphabetically. And then you square the h and get an h squared. Then you distribute this minus 5, minus 5r, minus 5h, and then you get your plus 6. Typically, nothing in here are like terms, so nothing here combines together or cancels. But then in the difference quotient problem that's probably coming up soon, then we do more to this, and then some of these things do cancel out there, but here none of them cancel. So we need a r squared plus 2rh plus h squared minus 5r minus 5h and plus 6. They're just trying to teach you the first step of the process with this kind of problem. Okay, without using a calculator, choose the graph that matches the function for x plus 5 squared plus 1. So the way I always do these is x plus 5 squared plus 1. X plus 5 squared plus 1. So the parent function for this type of problem is when you get rid of the excess numbers and you just have the bare bones of it. This is basically an x squared problem. There's an extra plus 5 and an extra plus 1 that affects it by moving it around to different things. But the essence of it is the x squared, which is a parabola shape right through the origin. So then each of these changes to the graph can move it around. And the way I always remember it is if you're with x, when you're with x inside of a grouping symbol like a parenthesis, an absolute value, a square root, anytime the plus 5 or minus 5, whatever happens to be, is literally with x, then it affects the x direction left and right. And you do it the opposite of the way it looks. Normally plus 5 is to the right, so this goes left 5. And then the one that's added or subtracted that's not with x, because it's not in the parenthesis with x, this one's not with x, so that affects y. Y's go up and down, and you do these ones like they look, so this one goes up 1. So I just want to grab this parabola and move left 5 and up 1. 1, 2, 3, 4, 5 to the left, up 1. That's where the vertex would be. That would be this spot right here. And then you just make the same shape from there. If there's a negative on the outside of the parenthesis, it would flip upside down. If there was a negative inside the parenthesis, it would flip left and right, which for a parabola, you wouldn't even notice that it flipped. And then if you have multiplying numbers or divided numbers or possibly multiplying by a fraction, which is like dividing, that causes stretches and shrinkings. But this didn't have that, so we just need to go left 5 and up 1, like graph C. Okay, complete the square. See, this is called the vertex form of a parabola because you can actually see the vertex. The vertex is the opposite of the +5, -5, and the +1 stays the same. So that's why you go to the coordinate -5, 1 and draw your vertex. It makes doing the graph easier. But the other version is when you have what's called the general or standard form, which is this form here. S of x equals -5x squared minus 40x minus 78. So from this version, you can't see anything about the graph. It's very hard to do the graph from this version. So we want to use completing the square, very useful algebra technique that will transform this into the vertex form. Then it's easy to graph it. Now there's this S of x over here, which is equivalent to y. We're not allowed to mess with that. So normally in completing the square, when you first learn that in algebra, you take this 78 and you move it to the other side of the equation to get it out of the way. Here we can't do that. So I'm going to factor out a -5 because you need to have a 1x squared in order to complete the square. So that's very easy to do. You just put the -5 here and you put the x squared there. But then the -40x gets affected by this -5. -40x divided by -5 is +8x. Then I put a plus blank because that's what I'm going to do to complete the square. And normally in completing the square again, you would move the 78 to the other side, but I can't. I'm just going to leave it here. And then I'll put another blank there instead of on the other side. So the big difference here is we can't do anything to the other side of the equation. So completing the square has 2 steps, and you kind of do them backwards once you've seen the process. The trick is you do half of this middle number. Half of +8 is +4. So x plus 4 squared always takes that format, x plus or minus whatever squared. And that's making it starting to look like the vertex form. And then 4 squared is what we put in this blank. 4 squared is 16. If there was nothing out here except for a 1, then you would put a 16 over in this blank too. But the same way this +8 is affected by the -5, this -5 distributes to everything in here. So -5 times x squared, that's how you get -5x squared. -5 times +8, that's how you get -40x. -5 times 16 is -80. There's really a -80 that I just inserted here. So we need to do the opposite and put +80 over here. +80 is the opposite of this -80 product that I just got right there. That keeps the equation in balance. If I'm adding and subtracting 80 at the same time, then I'm not changing what I have because 80 minus 80 is 0. And adding 0 to something doesn't change it. So now you can add the -78 and the +80 and you get +2. Here's the vertex form. And then very much like that previous problem, this would, if I need to do a graph, this is going to shift up 2 because that +2 is not with x. This +4 with x will move it left 4. The negative is a vertical reflection. It flips it upside down. And then the times 5, see, it could have been times 5 in the parenthesis. Then you do it reverse of the normal way. But here it's outside of it, so then you do it just like it looks. This is a vertical stretching times 5. If it was less than 1, it would be a vertical shrinking. And then that makes it look real thin. I don't know if this problem wants us to graph, but if it does, that's what we would do. They definitely want me to put it in vertex form though first, so complete the square, -5 x plus 4 squared plus 2, I think I had. Yeah. It doesn't look like there's a graph here, but that we could have done the graph. But the vertex is the opposite of this +4, which is -4, and then the 2 stays the same, -4, 2. That's why you would move left 4 and up 2. If you actually did the graph, you would go left 4. Well, first you'd flip it upside down, so think of an upside down graph. Then move left 4, up 2. There's the vertex. And then not only is it upside down, it's vertically stretched by 5, so it'd be really thin as it's going downward. The y values are falling 5 times faster than they normally do because of the vertical stretch. But we didn't have to graph this one. But we do need to know where that vertex is. It's over here at -4, +2. The vertex is right there. You can't see that from the original problem, but you can see it from the completed the square version. Okay, so given the graph of f of x, show the graph of f of ax where a satisfies the condition that it's between 0 and 1. Okay, so this would be multiplying by an a value inside with x. So that's going to affect the horizontal direction. And then if a is between 0 and 1, we're talking fractions like 1/2, 1/5, something like that. Multiplying by a half or a fifth is really dividing by 2 or 5. So if you're dividing, normally it makes things smaller, but instead it makes things bigger when it's a horizontal change. So you always do them the opposite. So it's not going to, here's the original graph. This first graph A is showing a shift up. That would only happen if you had a plus value outside of the parenthesis. It's not a shift up. It's not an upside down reflection. You would need a negative in front of the parenthesis. This one, it's a little hard to tell where this one's going, but it looks like, this looks like it just shifted one way or the other. So it's hard to tell which one the original one is. So I think this one is the original. So it's moving to the left a little bit, apparently. Well, maybe not, because they're both going through the origin. Let's see, maybe this is the one where it's shifting a little. One of these two, C and D, one of them is shifting slightly right or left, and the other one is the answer. We shouldn't be shifting. We should have a horizontal stretching is what's really going on. Because the A is less than 1. Normally, less than 1 makes things smaller, but for horizontals, they get bigger. So I think it actually is C because they both meet there is Y. Now it's hard to tell. I think the inside one, that's what the original one is. This is the original one. And then it's going wider this way and wider that way. It's getting horizontally stretched out. Where this graph D, I think, is the one that's shifted. It's a little hard to see it all. It's not even showing the whole graph, but this has been shifted a little bit one way or the other is what. I'm actually not sure because I can't see this whole graph. So this is either C or D, definitely. I already eliminated A and B. The issue here is I can't tell right there at that spot where the graph is continuing because they're both going through that. So is this going, I think it actually is shifted. So C is the one that's been shifted. Here is the original graph. And the other one's to the left of that a little bit. Yeah, so it's not C, it must be D. Where this is getting stretched out this way, and since we can't see it, it's getting stretched out that way too. But they stopped showing the rest of the graph for some reason. So this one's a little hard to tell between C and D, but I think C is definitely shifted to the left. A shift to the left would only happen if you added or subtracted an A value, not multiplied it. A multiplying amount is a stretching or a shrinking. In this case, if A is less than 1, then it's a stretching. Some of their graphs are a little hard to deal with like that. Okay, cubic graph. Remember on this, we want to go through our end behavior for polynomial graphs. End behavior. The way I always remember end behavior is the degree even or odd? Even degree versus odd degree. If you look at the two most basic functions of these, the best even function to remember is good old x squared. This is one we all know and love. Looks like that. So the end behavior is up on the left side and up on the right side. If you get a negative leading coefficient, then you do them both backwards and it's upside down. And then it's down on the left and down on the right. But you remember the positive one, that one you should have memorized. If it's negative, you just do them both backwards. Likewise, for odd degree, the best odd degree one is a cubic function. This is another one you should memorize from algebra. It goes up on the right like x squared does, but it goes down on the left when it's a positive leading coefficient. This is the one to memorize. Then if you get the negative version, you just do them both backwards. So now it's up on the left and down on the right. We have a positive x cubed, so that one should be down on the left and up on the right. Down on the left, up on the right. It's definitely not C where they're both up, and it's definitely not D where it's up first and down second. That would be a negative x cubed. So I can eliminate graph C and D right away. And also I can eliminate graph B because it has 1, 2, 3, 4 turning points. 4 turning points means you have to have at least a 5 degree. But this one only has 2 turning points. 1, 2. So definitely graph A because of the end behavior is correct and it only has 2 turning points, not 4 turning points. The degree tells you the maximum number of times you could cross or touch the x-axis. Notice this one crosses the x-axis once, twice, 3 times. And then one less than that is how many turning points you have. This one crosses or touches the x-axis once, twice, 3 times, 4 times, 5 times. So that has to be at least a 5 degree. Same deal here. Also be careful, make sure you check all the exponents. Sometimes they put them out of order. These exponents are in order, and the highest exponent is a 5 for this polynomial. So that's an odd degree, and it has a negative leading coefficient. So it definitely is up on the left and down on the right. Up on the left, down on the right. This one's definitely wrong. That's a positive odd, and this is a negative even right here. C and D are definitely out. Now, this one doesn't seem to be an x to the 5th because it doesn't have any turning points. It's just continuously going down, 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 down. It actually looks more like an x cubed where it just kind of is flat for a second there and then keeps going down. Where this one crosses the x-axis once, twice, 3 times. Now you don't always get 5 crosses, but it does have 1, possibly 2, 3, 4 turning points, where this doesn't have any turning points. So you don't always get the maximum, but it's more likely to be this one than that if there's an x to the 5th. There's too many terms here for this to just be a basic graph that just keeps going down, almost like a line. Okay, given the graph, give the possible values for the degree and the sign. Okay, well, the degree is definitely even because the end behavior, they're both up. Anytime they're both the same, it's an even degree. And then, because they're both up, it's definitely a positive leading coefficient. We can tell that for sure right away. It has 1, 2, 3, 4 x-intercepts, It has 1, 2, 3 turning points. So it very likely could be an x to the 4th power, where it has 4 zeros and 3 turning points. And it's definitely either 4 or higher than 4. Some even 4 or higher. It's not an x squared, and it's not any odd. So the degree has to be 4, 6, 8, etc. And it's definitely a positive leading coefficient because both of them are up. Okay, this fraction is fully reduced. No way to reduce it anymore. So anything that makes the bottom 0 would be a vertical asymptote, not a hole in the graph. So there's one and only one vertical asymptote. Type an equation, x equals -4. Don't just put -4. You have to set x plus 4 equal to 0 and solve for x. Subtract 4, x equals -4. Type an equation. It's real easy on a test not to read this blue part, and then if you just put a -4, they don't give you any credit for that. In an asymptote, it's always an equation, so you have to put x equals or y equals on any asymptote. The degree of the top is 0. The degree of the bottom is 1. Anytime the bottom has a bigger degree in a rational function, then you have automatically y equals 0. The x-axis is the horizontal asymptote. If the top is bigger, there's no horizontal asymptote. If they have equal degrees, then you divide the leading coefficients and put y equals whatever that is. This has no holes because the only way that happens is if the bottom cancels with the top, then the value that would have been a vertical asymptote turns into a hole instead. And then if I just use my two asymptotes, you can probably get the graph right. X equals -4 and y equals 0. We can eliminate any graphs that don't have those two. This is -4. And this is 0, so that this graph is possible. This graph is definitely wrong. It doesn't have an x equals -4 vertical asymptote, and it doesn't have a y equals 0 horizontal. This one does, and this doesn't. So graphs B and D are definitely out. And then all I need is one other point to tell is it A or C. If you didn't have multiple choice, you might have to plug a bunch of points in, but with multiple choice, all I need is one more point. The best other point to do is the y-intercept, because that's easy to find. Y-intercepts happen when x is 0. If I put a 0 in for x, I'm going to get -1 over 4, which is -1/4. Apparently, the graph A, since it's coming up from -infinity, and it's going to get close to but not touch the x-axis, that apparently is -1/4 right there. Whereas this one is coming down from positive infinity, so that's going to be +1/4 right there. So this is graph A because it has the correct x-intercept. The correct vertical asymptote, the correct horizontal asymptote, and the correct y-intercept. It doesn't have an x-intercept. Okay, see, don't get tricked here. When we get to the horizontal asymptote, this doesn't factor. There's no GCF here. This doesn't factor, so there's no way to reduce this fraction. There's no holes in the graph. But there is one x-intercept if you set 3x plus 20 equal to 0. Set the bottom equal to 0. 3x plus 20 equals 0. Subtract 20. And divide by 3. This is either an asymptote or a hole in the graph. Anytime you solve for the denominator equal to 0, you get either a hole or a vertical asymptote. This is a vertical asymptote, and then we need the x equals attached to it. It's a vertical asymptote because it didn't cancel with the numerator. Now this time they already typed the x equals for you. Last time they didn't, so you got to pay attention to that on your test. If they already have the x equals, then you just put the -20 over 3, but don't put a double x. But if the x isn't there, you have to type the x. So sometimes students get in the habit of the way the homework goes, and oftentimes they do the x for you, but if they don't, you have to put it. Now don't get tricked here. In the numerator part of this, they have it out of order. They put 4 minus 3x. the degree is the highest exponent. So the degree here is 1, the degree here is 1. They have equal degrees, so then you have to divide the leading coefficients. And that's a little misleading to say leading coefficient because students think 4 is the leading coefficient just because it's leading the order the way they wrote it. But if you rewrote this in the proper order, then you wouldn't get tricked by that. And then you can see it better that, yeah, the leading coefficients are -3 divided by 3. So that means the horizontal asymptote is y equals -1 because you should reduce -3 divided by 3 as -1. But it's not, actually I wrote it down wrong, but good that you saw the way I was doing it in case that happened. So it's not 3 divided by 3, watch out for that, it's -4 divided by 3. So the horizontal, I wrote it down wrong, but it's y equals -4 divided by 3 because you're dividing the leading coefficients. If they reduce, you should reduce them, but they don't reduce here, so -4/3. I had my 3 and 4 inverted. Okay, so we need an x equals -20 divided by 3. -21 divided by 3 is -7. So it's close to -7. That seems too close to 0 to be -7. This is going 5, 10, 15, 20. So it should be somewhere between the 5 and the 10 slot. So graph A is wrong because the vertical asymptote's not in the right place. This could be roughly -7. But the horizontal is -4/3, and this has a positive horizontal asymptote, so that's out. Here's correctly -7, roughly, and -4/3, that could be -4/3. And this is definitely wrong because it has the vertical right at 0, and the horizontal looks like it's 0 too. So just by knowing the two asymptotes, I can already tell this is the graph. I didn't even need the y-intercept. But you could easily get the y-intercept by plugging 0 in for x, and you would literally get 3/20, which is positive. It's pretty close to 0, but positive. So yeah, that is correct, that y-intercept right there. Okay, exponential graphs. So what I do for this is they eventually want me to do 5 to the x plus 1, but I'm going to do 5 to the x first. This is my parent function, the most basic one. So for exponential graphs, I always plug in -1, 0, and 1. And if I get log graphs, I actually do this first and then turn them around backwards. Anything to the first power is itself, so 5 to the first is literally 5. Anything to the 0 power is 1, and anything to the -1 makes it 1/. -1 with 1/5 is pretty close to 0. 0, 1 is right there, and then 1, 5 would be up here somewhere. This is the parent function graph. So the one they want me to do has one change compared to that. F of x equals 5 to the x plus 1. So I have one where there's a plus. That's going to be a shift, left, right, up, or down. The plus 1 is up there in the exponent with x. This plus 1 is up here with x. It could have been this. It could have been 5 to the x and a separate plus 1. Then it would not be with x. Then it would be y. So this would be a shift up 1 if you got this case. But this is a plus 1 with x, so that's a left or a right shift. And then you do it the opposite of the way it looks. The opposite of plus 1 is -1. So you want to move all 3 of these points to the left 1. This one will move right there. This one will move right to the y-axis literally. And that one will move over 1, even though it's hard to tell where it is. But I should definitely see a point going through -1, 1, and I should see a 0, 5 point in the choices. So it's definitely not upside down. This one looks like it moved to the right. They were trying to see if somebody thought plus 1 moves it to the right. It's hard to tell what that one's doing. I think it's this B graph here. And again, this is a little hard to tell because it's going 2, 4, 6, 8, 10. So it should go up 2, 4, 5. Right there at 0, 5. That's at least possible there. And then -1, +1, that's at least possible. And this graph here definitely doesn't go through 0, 5, so that's out. This one's already out, and this one doesn't go through 0, 5 either, so that's out. It must be B. That one's going through 0, 5, because it was actually 1, 5, and it got shifted to the left one. The 0, 1 got shifted to the left one. And then the -1, 1/5 got shifted to the left one right there. Okay, solve an exponential equation. 2 to the x equals 1 over 8. There's 3 levels of this kind of problem. This is level 1. Level 1 is when you can make the bigger base look like the smaller one. So I'm going to grab the smaller base, 2, and start listing powers of that. 2 to the first, 2 squared, 2 to the third. I found it. Sometimes doing that doesn't work. If this 8 was a 7 and I went 2, 4, 8 and skip 7, as soon as you bypass the number you're trying to reach, then that means this didn't work. And that could take you up to level 2 or level 3. Level 2 is where you can change both bases to a smaller one. Like say this was an 8 and this was a 4. Then I could change the 4 to a 2 squared and the 8 to a 2 to the third. But if it was a 7, then you wouldn't be able to change it to either the smaller one or both to a smaller one. Then there's another strategy for that. So I'm going to change 8 to 1 over 2 to the third power, the 8 changing to 2 to the third. Then if these 2's were at the same level, they would cancel out, but they're not currently at the same level. This one's in the numerator, this one's in the denominator. So I need to use a rule of exponents to get them at the same level. In the same way 5 to the -1 became 1 over 5. 1 over 5 can change to 5 to the -1. It goes both ways. So I can change 1 over 2 to the third to 2 to the -3. That's what a negative exponent does. Makes it switch places in the fraction. Now the 2's are at the same level, so now they cancel out. And x equals -3. Okay, the interest formula. Just need to write this down somewhere before you start your test. The interest formula is A equals P, 1 plus R over, I'm trying to remember if your book uses M or N. Some books use M, some use N. It's not really a big deal, but I think we had M here, if I remember right. MT. Or if you put N's, it's not a big deal. M or N, whichever, some books use M, some use N. It just stands for the number of times per year that you do the interest. So it really doesn't matter if you call it M or N. I'm used to calling it N, but I think this book calls it M. Either way, I like N because it's number of times per year. Number starts with N, but either way, it's the same formula. Okay, we're investing $10,000 right now. That's the present amount or the principal. The time is 4 years. The interest rate's 5%, and then we're going to do this annually, semi-annually, quarterly, monthly, and continuously. So how much will we have in the future? A is the future value. P is the present value, 10,000. The interest rate's 5%. That's 0.05. First, I do this annually, where the number of times per year is 1, and then we're doing it for 4 years, I think it said. Yeah, 4 years. So annually is nice because then the 1's in the denominator and the exponent don't matter, and you just get 1 plus 0.05 to the 4th power. Or what would be 1.05 to the 4th power. 1.05 raised to the 4th power times $10,000. Your account will be worth $12,155 and maybe 6 cents 4 years in the future from now. $12,155 and 6 cents. Now maybe they're going to say round to the dollar, then $5, but it does say round to the nearest cent. So 12,155 and 6 cents. That's for annually. So then we're going to do this 3 more times with this same formula. Next, we're going to change this and this to a 2. That's what semi-annually is, twice a year. Everything else stays the same. So I'm going to get an A equals 10,000, 1 plus 0.05 over 2 to the 2 times 4. So 0.05 divided by 2 is 0.025. And if you don't know that, you can do that first. 0.05 divided by 2 is 0.025. And that makes the parenthesis part 1.025. And of course, 2 times 4 is 8. So take your 0.25, add 1 to make it 1.025. Raise it to the 8th power, then multiply by 10,000. 12,184, and if I want nearest cent, I'm going to have to add 1 to this 2 and make it 3 cents, because there's an 8 here. 12,184 and 3 cents, which is about $30 higher than the previous time. 12,184 and 3 cents. A little less than $30 more. Quarterly, now you just change the 2's to 4's. 10,000, 1 plus 0.05 over 4 to the 4 times 4. So these two 2's right here changed to 4's, everything else stayed the same. So do the fraction first, 0.05 divided by 4, then add 1. You always want to get the parenthesis down to a single number first. 1.0125. 1.0125, I think I said. 1.0125, yes. 4 times 4, you can do that in your head, hopefully, 16. So raise this to the 16th power. Multiply by 10,000, and it should be a little higher than the last answer. 12,198. Now this 89 cents, there's a 5 here, so you have to add 1. Think of adding 1 to 89 instead of just adding 1 to 9. Some people add 1 to 9 and it's a 10 and then they carry a 1. You can do that if you want, but it's easier if you just say add 1 to 89 and make it a 90. 12,198 and 90 cents. Oops. 12,198 and 90 cents. Okay, one more time with this formula, and then there's a different formula for the last one. Monthly is 12 times a year. So change these two 4's right there and there to 12's. 10,000 times 1 plus 0.05 over 12 to the 12 times 4. So I want to get the parenthesis to be 1 point whatever, and then 12 times 4 is 48. So inside the parenthesis, you're doing the division first, order of operations. You divide before you add. So divide first, 0.05 divided by 12. See how that's a big messy decimal? But add 1. Now, you can round it on your paper, 0.00417. But if you leave it unrounded in your calculator, that's usually better for getting the answer right. I'm not going to round this here, and then I'm going to raise it to the 48th power. Then multiply by 10,000. Otherwise, if you round it even this much, you can be off a little bit, especially when they want you to round to the penny. So 12,208 and 95 cents. The next digit is a 3, so you don't have to add 1. 12,208 and 95 cents. if you did something like, if you just rounded this to 1.004 and tried to do it, 1.004 to the 48th power times 10,000. See, it's totally a different answer now. Instead of 208, 12,208, you only get 12,100. You just cost yourself $100 just from rounding. So that's why you don't want to round in the middle of the problem. Okay, so 12,208, which is a better answer because it should be higher than the last answer. 12,208. That wasn't it. It was over here. 12,208 and 95 cents. And then the last one should be even a little higher than that. So this is continuous compounding. That's the best you can hope to do if you're trying to make money. I always remember this as the shampoo formula. PERT, P, that's principal, times E, that's special Euler's constant, 2.718, raised to the RT power. It's just a different formula than the other one, but a little less stuff to do. 10,000 E to the 0.05 times 4. 0.05 times 4 is exactly 0.2. So now I'm going to do E to the 0.2. My calculator has an E button. E raised to the 0.2 times 10,000. And hopefully it's a little bigger than the previous answer. 12,214. And 02, but then there's a 7, so make that 03. 12,214, 03. And see, it is about $6 higher than the previous answer. So that's not a guarantee I did all these right, but this is what should happen is the answer should be getting bigger and bigger and bigger as you go. The more times you compound in a year, the more money you make. And that's why they're making you do all 5 of these parts to show that. Okay, write in log form. So remember this, you're not solving anything here. This is just a quick rewriting it. We should know that 5 to the third actually does equal 125. They wouldn't give you a false statement. 5 to the third power is 125. And this is the exponential form. We want to write it in its equivalent log form. Which obviously has log in it. In the exponential form, there's 3 parts, and then in the log form, there's 3 parts. Everybody knows the raised up number is called an exponent. And then most know that the big number attached to that's called a base. So if you know where is the base, where is the exponent in the exponential form or the log form, then you can translate these back and forth. In a log, the base is written down low. Log base 5 is the way we read that. And a log is an exponent, so the exponent goes over here at the equals portion. That's the 2 locations in a log. And then the only thing I haven't used yet is 125, so that must be the number in the domain slot. So it's log base 5 of 125 equals 3. That's equivalent to 5 to the third is 125. And they already did the base 5 for me. Log base 5 of 125 equals 3. Now you kind of do that for this problem here. There's just a blank instead of all 3 slots filled in. Log base 4 of 256 equals blank. So for blanks, I like to put an X there, and so that way I have all 3 of my things. I have 3 parts of a log here. I want to write the 3 parts of an exponential. So in a log, the down low number is the base. In exponential, that's the regular size number. A log is an exponent, so the exponent's obviously the one that goes up high. And then there's only one thing left, and it's the one thing I haven't used yet, 256. So now we go back to this kind of problem right here. And I'm going to try level 1, where I try to make the bigger base look like the smaller one if I can. And if I can't, we'll move up to level 2 or 3. Is there a way to make 256 look like a 4 is the first thing I would try to do. So 4 to the first is 4. 4 squared is 16. Now maybe you need a calculator to do the rest. But 4 to the third, 64. 4 to the fourth. Aha, 256. So we can change 256 to be 4 to the fourth. Those are equivalent. And unlike that previous problem where the 8 was in the denominator, these are at the same level. So the 4's cancel out right now. X equals 4. A lot of 4's in that problem. X equals 4. Okay, remember this rule? If you take natural log, that's actually log base e, even though we don't write it that way in the end. But natural log of e to the 1/9, natural log is actually log base e. And then one of the properties of log is if the base of the log equals the domain value, which usually doesn't happen, but in the rare cases that it does happen, then all of this cancels out, and this is literally the answer. The exponent becomes the answer. So ln and e just cancel each other out, and the answer is literally 1/9. Very easy problem. Don't even have to do any work if you remember that. ln, and this is why in equations we sometimes add a log to both sides of an equation to make this happen. If we have an equation with an e in it, one way to solve it is to put an ln on both sides of the equation, and then the ln and the e cancel out. We'll probably see one of those coming up here soon. Log base 6 of 2x minus 9 equals 1. So I'm going to do this like 2 problems ago. I'm going to do this like number 16. I'm going to try to change it from a log to an exponential, and then maybe it'll work out nicer. It's harder to work directly with logs, so usually it helps to change them back to exponentials. Log base 6 of 2x minus 9, this time the x is in the domain slot, equals 1. So remember the x, we had an x over here. Even the base can be an x, or the x can be in the domain. It doesn't really matter. I'm going to grab the base first. The base of this log is 6, so that's the first thing you write in exponential. A log is an exponent. There's the exponent. And I haven't used that yet, so 2x minus 9. Now you're just solving an algebra problem from high school. 6 to the first is 6. It could have been something like 6 squared, and maybe you'd have to change it to 36. Add 9. 6 plus 9 is 15, equals 2x. Divide by 2. X equals 15 over 2. And they usually prefer that, never put a decimal unless they ask for it. So it doesn't say anything about decimals or fractions, but they usually don't like decimals, so I would be safe and put the fraction 15 over 2. Maybe they'll take 7.5, but sometimes they get picky for that. In calculus, it's usually not good to put a decimal unless they ask for it, so I would do that. Okay, that's the end of chapter 2. 1 through 18, those were chapter 2 problems. Now we're into chapter 3 where limits come up. So this is the rule about limits. Whenever you're looking for a limit from the graphing method or the table method, then you have to be thinking of the left and the right side of limits. And only if their answers match each other does the overall limit have an answer that would be that answer. But if the left side of the limit is 7 and the right side of the limit is 9 at the same x value, then the limit does not exist. That's literally what this rule is telling you. If the left side of the limit was 7 and the right side of the limit was 7, then the overall limit would be 7. That's what you hope happens in the graphing or table method. Sometimes there's algebraic methods where you don't have to worry about left and right sided limits, but usually it's good to be thinking about them to see if they match or not. And then remember in section 3.2, then we also worry about, does f of 4 match my limit answer or not? Here we don't really care about that, but f of 4 may or may not be 7 or 9. It could be something else, or it could even be undefined. But at this point, it doesn't really matter. Okay, so 19 was just about the rule of limits. 20, you're actually going to do the graphing method. So first they want me to go close to 1. And they're not making you answer the left and right side of limits, but you should be thinking that. So the left side of the limit, when you get really close to 1, like 0.99999, you would go down and you would be right down and to the left of that circle. You'd be this little line coming out of that circle. So that means you'd be a little bit below whatever y value that is. -1, -2, -3. The left-sided limit is -3. The right-sided limit, come here from the right till you get close to 1, 1.0001. Again, you would go down and you would be touching right there, a little bit above that circle. But that's still close to -3. The left-sided limit is -3. The right-sided limit is -3. So the overall limit at 1 is -3. But f of 1 exactly is right there. F of 1 is -1. That doesn't matter for this, but in section 3.2, this is showing that the graph is not continuous at 1. Even though the limit had an answer of -3, checklist item 1 works. Checklist item 2 works. F of 1 equals -1. They both have answers, but those two answers disagree with each other, so that's why the limit exists, but that's why the graph is not continuous at 1. And that's not what this problem's about, but I'm just refreshing your memory on that. So now do another limit close to 3. So get really close to 3. From the left, you would literally be right there, just slightly below 0. The left-sided limit is 0. But coming in from the right, close to 3, you'd have to go down here to touch anything on the graph. So now you're slightly below -2. The left-sided limit is 0. The right-sided limit's -2. They disagree with each other, so the limit does not exist. That's all this problem wants you to do. But if you worried about section 3.2, then you would say, okay, this is not continuous here because checklist item 1 failed. Even though checklist item 2 would work because f of 3 equals 0 exactly. So the function has an answer, but the limit doesn't. And therefore, there's no way the function answer could agree with the limit answer because the limit answer doesn't even exist. Clearly, the graph was discontinuous at those two spots because you had to pick your pencil up. Okay, then the next thing we can do is properties of limits. Algebraic techniques allows us to not necessarily worry about left and right-sided limits. So this is 21. If you get a limit of a polynomial, it always is continuous. So then you can just do f of whatever the number is and you'll get your answer to your limit. Then the limit answer will always agree with the function answer. If you get a rational function, you can basically do that too, unless it causes the denominator to be 0, which it does in this case. But that's the first thing to try in a rational function is, could I just do f of 6? If I do f of 6 and get an answer, that will always be the limit answer in a polynomial or a rational function. But if you do f of 6 and get undefined for the answer, then the limit could still have an answer, actually. It's just that the function doesn't have an answer. And it could be that it's discontinuous there, and that's why you're not getting a function answer, but it could still have a limit answer. So yeah, unfortunately, plugging 6 in causes this to be undefined. The function doesn't have an answer exactly at 6 because there's actually a hole in the graph there. And that's because I can factor the top into a difference of squares. And that cancels with the denominator. So instead of getting a vertical asymptote at 6, I get a hole in the graph at 6. But it creates a new function of literally just x plus 6, which is a polynomial on its own. The original function was a rational function. The fraction. And that was undefined at 6. But a reduced version of it creates kind of a new function that I'm given a different name, g of x. This has no issues with it. So the limit as x approaches 6 for this new function is going to have an answer because this is a polynomial. So therefore you can just plug the 6 in. And if you can reduce a problem, even though it causes it to be a new problem, the limit doesn't change in a reduced version. The function value can change in a reduced version, but the limit value doesn't change. And if you knew how this graph looked, it would have a y-intercept of 6, y-intercept of 6, and a slope of 1. So this would be a line going up 1 over 1 until you get to an x value of 6. Then there'd be a hole in the graph there. And if you're starting at a y value of 6 and you go up 1 over 1 6 times, then your y value at that spot will be 12. And if you're a little to the left of 6, you're going to be slightly below 12. If you're a little to the right of 6, you're going to be slightly above 12. The limit is 12 there, even though f of 6 is undefined. And the graph is discontinuous if I was worried about section 3.2, because there's a hole in the graph. I have to pick my pencil up to go over that hole. But that's okay for the limit. The limit doesn't care if the graph is continuous or not. So this is why limits were such an important concept in calculus when they first discovered these 400 or 500 years ago, is f of 6 is undefined. So to a person that first encounters this, they'd be like, oh, there's no answer there. There's no point in worrying about this anymore. But the rest of the function exists and is interesting. There's a line everywhere else except that one little tiny spot. And even though there's nothing at that one little tiny spot, it's basically what the limit's saying is the answer would roughly be 12 if the graph existed there. If only there wasn't a hole there, the answer was going to be 12. That's what limits are all about. So when the function doesn't have an answer and the limit does, that's kind of why limits are so important. They let you know what the answer would have been if you could have got to that spot. Where up to that point, everybody just gave up and said there was no answer. So the limit is 12. It kind of tells me the function is about 12 in that spot, even though I can't get that 12 directly from the function itself. Okay, then if you go out to infinity, I can't plug infinity in as the problem. If I did, I would get infinity over infinity into the original function. Limit as x approaches infinity. Going out to infinity is kind of what a horizontal asymptote is about. So if you know what the horizontal asymptote to this problem is, that ends up being the answer to this. But here's why that works, actually, instead of just saying, oh, do that. 9x squared minus 3x plus 1. So you could literally plug infinity in, but infinity squared is infinity and plus infinity is infinity. There's nothing bigger than infinity. So it causes both the top to be infinity and the bottom to be infinity. Infinity divided by infinity doesn't make sense. So that doesn't work, and we can't do that. So the trick is whatever the highest degree is, x squared, and it's okay if there's a tie for the highest, but sometimes only one of them is the highest. Whatever the highest one is, that's what you divide each and every term by. And you don't need the 9, just the x squared part of it. Divide every term by an x squared, and then you're not changing what you started with because you're doing the same thing to everything. You're really multiplying, and you're multiplying the top and the bottom by 1 over x squared by doing this. So then you can reduce this, and remember in limits, if you reduce things, the limit answer doesn't change. So sometimes in the original it's hard to do, but if you do a reduced version, then it's easier to do. So the x squareds here would cancel, so I would just have a 9 for that slot. I lost my x here, but okay, this x would cancel one of these two, so you would get 2 over x for that part. These would cancel, you just get 9. Same deal here, you would lose 1x and get 3 over x. And this wouldn't reduce at all, 1 over x squared. Now when you plug infinity in, something divided by infinity gets really close to 0. 2 divided by infinity is virtually 0. So it makes it become 9 plus 0 over 9 plus 0 plus 0. All the parts where there's an x in the denominator, even if they're squared, all three of those parts get really close to 0. And the 9 stay the same, so 9 over 9 equals 1. This limit answer is 1, and in fact, if you knew how horizontal asymptotes worked, if the degrees are the same, the horizontal asymptote is y equals the leading coefficients divided by each other. 9 divided by 9 is 1. So the horizontal asymptote y equals 1. That's what's happening way out at infinity. So the limit equals 1 because of that also. Okay, discontinuous. We can see from the graph that one hole got plugged up. Make this bigger. There could have been two discontinuous spots because we had a linear piece, and then apparently there was a hole there, but the linear piece with its closed circle landed on top of it and closed it up. And then there's a horizontal piece with another open circle, and then another linear piece after that. And there's a dot up here, but it didn't close the circle. So there's one and only one hole in the graph left, right there at x of -2. So an a value of -2, it's the only discontinuous spot. And then we want to go through our checklist items there. The left-sided limit near -2 would take you down to -1, exactly. The right-sided limit, you'd be slightly above -1, but that's still close enough to say -1. So f of a would actually equal this y value up here. 1, 2, 3, 4, 5, 6, 7. F of -2 is actually 7. The function has an answer, and it's 7 at -2. But the limit, the left-sided limit, is -1. The right-sided limit is also -1. That's why the limit has an answer of -1, the overall limit. So checklist item 1 worked, the limit has an answer, -1. Checklist item 2 worked, the function has an answer, 7. But because the limit answer and the function answer disagree with each other, then checklist item 3 fails. And the graph is not continuous there. So it's this one C here where the limit answer equals the function answer. That's checklist item 3. But that failed here. They didn't equal each other. 7 did not equal -1. It was defined, and the answer was 7. The limit existed, and that was 1. But checklist item 3 failed. Okay, here's one where we have to do it ourselves. So this is a rational function, and nothing reduces or cancels here. So no holes in the graph. In a rational function, it's continuous everywhere except for holes in the graph and vertical asymptotes. We don't have any holes in the graph, but there would actually be two vertical asymptotes here. 0 and 5. 0 and 5. There's two vertical asymptotes. And the function is undefined at those two spots because they're asymptotes. But we don't know necessarily if the limit exists or not automatically, because it really doesn't exist, but they consider getting an answer of infinity or negative infinity to be separate from just technically doesn't exist. So if one graph is going up and the other one's going down at these spots, then you would say the limit doesn't exist and it's not infinity or negative infinity. But if it's going both in the same direction, then it doesn't really exist, but we can specify that it's infinity. So this is one where there's a vertical asymptote at 0 and another one at 5. So we would like to know, is the graph doing something like this? The one in the homework we had was like that, and then this graph here was upside down. So then this would be positive infinity, but this would be negative infinity, so that's where you say it does not exist. But if the inner graph went something like this, which happens sometimes, if this is infinity and this is infinity, then you would specify that the limit is infinity, actually, even though technically infinity doesn't really exist either. So that's the only thing we have to worry about is, are these both going at the same infinity or negative infinity? Because this one could be going down here and this one could be over here too. If these are both down, then the limit's negative infinity. So these could be hard to do in general if you don't know how to graph this, or it can take a while even if you have to do it by hand especially. So if you had access to technology on your test, this would help to have a graphing calculator. But if not, you're just going to have to do it slowly by plugging in various x values close to 0 and 5. So I'm going to put in my y1, I'm putting parenthesis 6 plus x parenthesis for the numerator, divided by, and then since the denominator has two things, I'm going to put an extra parenthesis for the whole thing, x parenthesis x minus 5 close parenthesis close parenthesis. This way I have the numerator in a parenthesis and the denominator in a parenthesis. Graph, and if I can just see where they're going towards. See, it's a little hard to tell, but I think I did take my axes off. Yeah, the axes aren't on. So see, it looks like they're both going up to infinity there, and they're both going down to negative infinity there. So, and we could check that by going to a table just to be sure. If I delete my values in the table, if I'm really close to 0 from the left, like negative 0.00001, the y value for that is very, very large, so that's like infinity. So then what if I go to 0.0001 on the right? Is it also positive infinity? No, it's negative infinity. So the graph was a little bit deceiving there. So that's what I thought was happening, is that usually on the graph like this, the table method was a little more definitive here. When I'm coming in from the left, it's shooting up way up to 12,000. So that's infinity. But when I come in from the right, it's going down to negative infinity. So here it's positive infinity. Here it's negative infinity. So therefore, that does not exist. And then 2, 3, 4, 5. So then what I would do is try like 4.999 and 5.001. So this, even if you don't have a graphing calculator, at least you could do 4.999 with any calculator. You could just figure out what's the y value for that. It's negative 12,000, negative 2,000, whatever. So that means, see how this is going to go back down here. And then if I try something like 5.001, is it a big negative or a big positive? It's a big positive. Positive 2,000. So that means it's up here. So the graph's a little deceptive. Sometimes it has trouble around asymptotes. So that would be a better way to do this problem, because all I had to do was 4 calculations. If you plug in negative 0.0001, is your answer a big positive or a big negative? Then plug in positive 0.0001, big positive or big negative. I got big positive here, big negative over there. Then I plugged in 4.999 and 5.001, and I got a big negative first and a big positive second, so that's definitely the limit does not exist at those spots. There's 2 discontinuous spots. And here it is, G. 2 discontinuous spots, 0 and 5. That's where the 2 asymptotes are. And the limit does not exist and is not infinity or negative infinity for either one of them. So there's a lot of choices here, because you could have where you have your 2 discontinuous spots, and maybe the smaller limit is negative infinity and the larger limit is positive infinity. Or maybe one has an answer and the other one doesn't exist, or vice versa. Okay, finally we have this piecewise function. So there's a quadratic piece in the middle of the graph that has 2 closed circles. So what would be happening there is something like so, a closed circle, part of a parabola, closed circle. And then there's two horizontal pieces that will have open circles, one going to the left, one going to the right, something like that possibly. This is if all three pieces are separated from each other. Or this open circle could land there, and or this open circle could land there. Both or neither, or one of them. So that's what would make it either all continuous or all discontinuous at those two spots. So it's continuous everywhere except at possibly -3 and possibly at 1 and or 1. So the best way to tell is if you plug -3 into this middle function, do you get +2 for an answer? If so, then that connects up with it and it would be continuous there. -3 squared, though, is 9. 9 plus 1 is 10. So that's not continuous at that spot. And then when I plug 1 into the middle function, do I get +2 there? Or this could have been a different value than 2, but 1 squared is 1. 1 plus 1 is 2, so it actually is connected up there. So you have this open circle at 2 going to the left only, but then there's a closed circle at 10 for the parabola part. And there would have been another closed circle at 2, but the open circle at 2 landed right on top of it and filled it in. So it is continuous when x is 1, but it's not continuous when x is -3. So this is graph A. It's only discontinuous at -3. It could have been both, but it's only -3. And then the limit from the left at that spot is right here, 2, but the limit from the right is up there at 10. The left-sided limit is 2. The right-sided limit is 10 for my one spot that was discontinuous. Okay, so that's why it's not continuous there. If I was looking to see if they were going to say what's the overall limit, we would say it does not exist, and that would fail checklist item 1, and that's why it's not continuous there. But that's the point of this, is they already, if you say that it's discontinuous, then they already know that these limits are not going to agree with each other. Okay, so I've answered all 25 questions. We're now going to submit the quiz. So I'm down here at submit. And we'll see if I got 100 or not. Yes, I want to do that. 92, I missed 2 questions somehow. Okay, 14. And see, if you're happy with a 92, then you never have to do it again. If you aren't happy with a 2, I'm at a 92, then you'd have to redo the whole thing. Something went wrong here. 12,000. Oh, I see what I did wrong. Okay. They only wanted the interest. I didn't read this closely enough. See, this is what can happen, is you can miss a problem because I was rushing through it a little too fast. Trying to keep this video under an hour and a half. We're getting close to an hour and a half right now. But what I should have done on all these problems, you need to go back and subtract 10,000 on each one. The 10,000 is your money. So really what it's going to do is just going to eliminate the front of this. So it should have been 2,155.06, not 12,000. The original 10,000 was my money. So notice it says you answered 12,155.06, and it was supposed to be 2,155.06. So 12,184.03, but it was just 2,184.03. So I can check that all 5 of these would have been correct if I was paying attention closer. That one's right. 208.95, yep. And yeah, they would have all been right. I wasn't paying attention closely enough. But see, that's what's good, is I messed it up, and now you guys can hopefully get it right. Find the interest. It didn't say find the future value. I was doing future value. I just assumed that's what they wanted. But they said find the interest. So if you're not paying attention, you could miss a problem. If I was taking the test, I would have only gotten a 92 because I messed that up. On number 14, I did everything right, except I forgot to subtract the 10,000 on each answer. And then 24, what happened here? It's the function is discontinuous at 0 and 5. I thought I put that. Two values. I could swear that's what I put in there. I know I said that. The function is discontinuous at 2x values, and it looks like I typed this. Maybe I didn't click it enough, but why it's saying I clicked G somehow. I don't remember that, actually. I definitely didn't put that it was discontinuous over an interval, but it was correct that the limit did not exist, and it's not infinity or negative infinity. I know I said this choice, but either I didn't click it properly or something weird happened. But at least we did that problem right. It weirdly counted me wrong. I'm not sure why. I haven't seen that before. Occasionally I have seen where a student has emailed me and they're like, you know how I was just clicking on number 14? Sometimes it's very, very rare, but occasionally a student has said, they've sent it to me and it says they answered 2,155.06. And then when you click this, actually, this is the right answer, and you have to click it to see what you put. But I've literally seen it sometimes where it says the correct answer is 2,155.06, and you answered 2,155. I've seen that happen sometimes, and I can't explain why it would mark it wrong if it was actually right. This one was actually wrong, but I've seen that. I don't know if that happened on number 24. And if I did click, maybe I can go back and watch the video and see what I clicked there, but if I click the wrong thing, then yeah, I deserve to get it counted wrong, but I know I said this correctly. On a test, you don't get to say, I meant to say this answer, so I would get a 92 for this if I messed that up. But at least I explained it correctly. There were two values that were discontinuous, 0 and 5, and the limits were not infinity or negative infinity because one was going up and one was going down. So I'm not sure what happened on number 24. But if I was happy with a 92, then I wouldn't have to do this ever again, or I could just practice the ones that I missed. And my mistakes were careless mistakes on my part, so that counts for if I was getting a grade for this. But at least then you feel comfortable that you understood what was supposed to happen and what you should do on a test. It's okay to mess up on a review and learn from it, and then not make that same mistake on the test, hopefully. So 14, I forgot to subtract the 10,000 because they did ask for the interest, not the future value. And I'm still not sure what happened on my 24 because I had it right on my paper, but I apparently didn't put the answer in correctly, which that counts if that actually did happen that way. If it was some kind of computer glitch, it's hard to know that at this point, but it's a pretty good program. I don't get computer glitches all that often, but it has, in a rare cases, it has happened before. So that's it, unless you have any questions. And now you should be all set for the test at the end of this week. You get a 2-day window for the test, either on Thursday or Friday. So a little bit of flexibility there on tests. And if you want to do it on Thursday and have your weekends free, that's fine. That gives you the chance to, if we're kind of treating this class like it's a Tuesday, Thursday class, and that way you can be done on Thursday and have your weekends free. Or more students will take it on Friday just so they have more study time, more practice time with the review. So if you have any questions, email me, but otherwise, good luck finishing the homework, the review, and whenever you take the test on Thursday or Friday.